Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the VLSI technology. In that we are discussing the chemical vapor deposition and the dielectric thin films. So I hope you all have watched all of the previous videos till now on the chemical vapor deposition. If not, it is highly recommended that at least you go back and watch all of the previous videos on the chemical vapor deposition. So today our topic of the day is the thin film characteristics. We are going to find out the various characteristics of the dielectric thin film that we are depositing on the given wafer. So we have various characteristics for the given dielectric thin film. So most of these characteristics we are going to find out, and these characteristics are used to define the particular dielectric thin film that we have on the given wafer. Okay, so the characteristics are refractive index, thickness, uniformity, particles and the stress. All of these are going to determine what kind of film that we are having and what application it can be used in. Okay, so for particular characteristic I have a particular application. So now I hope you understood why we are studying about this topic. Okay, so you must know that we are finding out the different characteristics so as to find out the different applications of the particular dielectric thin film that we have deposited. So the first characteristic is the refractive index. We all have heard about this term. Some of you might be aware about this term. So the refractive index is equal to the speed of the light in the vacuum divided by the speed of the light in the given film. So it is the ratio of the speed of the light in vacuum and the given film. So now if I have three types of material, the first material is vacuum, the second material is air and third material is glass. Right, if I need to compare the refractive index, I need to know the speed of light. So I know, okay, it is a very common thing that the speed of light in the vacuum would be highest among these three, speed of light in the glass would be lowest among these three, and the speed of light in the air would be intermediate. Okay, so now if I am dividing the speed of light in vacuum, which is a constant term, with the highest value, which was the speed of light in vacuum itself. Okay, I have considered the vacuum as the highest value of the speed of light. You can consider any other substance as well. So speed of light in vacuum, a constant, is divided by the maximum value. I am going to get the minimum value. Okay, the output would be the minimum and the refractive index of the vacuum would be the minimum. And let me tell you, the refractive index of the vacuum is a relative quantity. It is used for finding out the refractive index of the another substances as well. So if I want to find out the refractive index of the glass, I am finding out it in the relation of the refractive index of the vacuum. Okay, this thing must be clear. So now if I am talking about the refractive index of the glass, as I have told you, speed of light in the glass would be the least. So when the constant is divided by the least value, I am going to get the maximum value. So refractive index of the glass would be maximum and the refractive index of the air would be intermediate. Okay, so I hope now you can do the comparison on your own if you know the speed of light in the different substances. Okay, so this is how we can calculate the refractive index practically. So if I have any incident light, this is my vacuum, let's suppose, and which is having the refractive index N1. I know the N1, the refractive index of the vacuum is known to me. Okay, so now incident light is making any angle theta1, okay, with the normal. So now when it is getting refracted inside, it is making any angle theta2 with the normal. Okay, so now this is the film which is having the refractive index N2. So according to the Snell's law, N1 sin theta 1 is equal to N2 sin theta 2. Okay, now here I know N1, as I have already told you, N1 is the refractive index of the vacuum, that we know the theta 1 incident light angle with the normal, I know that, and I know theta 2 as well. So with the formula I can find out the N2 easily. Okay, so this is how the refractive index calculations can be done. And now coming to the information from the refractive index, what all inferences I am going to derive from the value of the refractive index. This is a very important thing that we must know. If I have the increment in the refractive index, you can see the refractive index is 1.46 here for the silicon, 2.01 here for the silicon nitride, 4.0 for the polysilicon. right? So here we are having high nitrogen and the high silicon level but the less oxygen level. Here in the silicon nitride I have high silicon level, less oxygen and the less nitrogen level. In the polysilicon I have less oxygen and the less nitrogen level. So all of these inferences we can derive from the value of the refractive index. So coming to the measurement technique, how we can measure the refractive index in a practical manner with the help of the ellipsometry technique. So ellipsometry is a technique with the help of which I can either measure the refractive index or I can measure the film thickness. So both of them are really important. So now if I have any linearly polarized incident light, I am sending the linearly polarized incident light towards the wafer. It is incident on the wafer at a particular angle. Now some of it again will be getting refracted and some of it will be getting reflected. So now if I am seeing only the reflected light, so it will be converted into the elliptically polarized light. So now the linearly polarized light is converted into the elliptically polarized light with the help of reflection from this thin film. If I have different types of thin film, the level of elliptical polarization will be different. Okay, this is how we can measure the refractive index of the given thin layer. Okay, we can measure the thickness as well. So this is the illustration of the prism coupler. Here we have a prism to measure the refractive index. Okay, so you can see this is my thin film, this is my substrate which is on a coupling head. Okay, so this is my prism and I am sending a laser light. So laser light is moving from the vacuum. Let's suppose the vacuum was there here. Okay, so now from the vacuum it is moving to the glass. The prism is made up of the glass, so the light will bend and now it is reaching to the substrate. Some of it will be getting refracted. So the refracted light will get trapped inside the substrate. It will be getting totally internally reflected and it will start traveling towards the end of the substrate. And some of it might be getting reflected and here again it will be reaching to the interface of the glass and the vacuum and it will be moving away from the normal and it will be reaching to the photo detector. So this is the full illustration of the prism coupler, and with the help of photo detector we can easily find out the angle, and with the angle we can easily find out the thickness or the refractive index of the thin film. Okay, so now the reflected light intensity versus the incident angle. The photo detector can easily find out the intensity of the reflected light, but at different incident angles. If I change the incident angle, okay, so the first incident angle in which the laser light is moving here, okay, so I can have another incident angle as well. So laser light will be moving from this angle or another incident angle as well. So now if I am changing the incident angle, what will happen? The phase will change, the constructive and destructive interference are going to happen. So you can see here, if I am changing the incident angle, here I have the constructive interference, and which means the reflected light intensity would be highest here. Here at this point I will be having the destructive interference, and according to which I will be having the reflected light intensity to be minimum over here. So this point is called the mode, okay, the point at which I will be having the destructive interference. Again here I will be having the constructive interference, here I will be having the destructive interference. So I can easily find out the number of modes. Okay, so this is how my Matricon model 2010 prism coupler would be looking like. This is the practical prism coupler that we have. Okay, here on the screen you can see we have the different graphs for the reflected light intensity on the basis of the different angle of incidence, and you can easily calculate the number of modes from this graph as well. Okay, so now comparison of the two methods. So first is the ellipsometry coupler and second is the prism coupler. So now if I am using the ellipsometry coupler, I need to know at least the rough film thickness beforehand. Okay, at least the rough film thickness, which means I need to know the approximate film thickness. I need not to know the exact film thickness, but at least a rough measurement of the film thickness would be there beforehand only. So it can measure the thickness if refractive index is known. Okay, it can measure either refractive index or thickness. If any one of them is known, then it can measure the other thing. So now coming to the prism. So prism needs certain thickness of the film which is greater than 3000 angstrom. So it can measure only those films which are thicker than 3000 angstrom. It can measure thickness if film thickness is enough to support enough modes. If it is not having less If it is not having large number of modes, it is not going to measure the thickness of the film. So it measures the film's thickness only when it is having large number of modes. So now coming to the thickness measurement. I have already talked about the thickness measurement. So it is one of the most important measurement for the dielectric thin film process, because if I have different thickness of the dielectric thin film, the basic application is going to change. Okay, we know the SiO2 layer which is used for the passivation is having different thickness. The SiO2 layer which is used for the oxidation mask, for the diffusion mask, or for ion implantation mask is having the different thickness. So the thickness is actually denoting what is the practical application of the given dielectric thin film that we have deposited. So we need to know the exact thickness of the dielectric thin film that we have deposited. So it determines the film deposition rate, it also determines the wet etch rate and also the shrinkage. So the dielectric thin film measurement can be done with the help of the reflection. So you can see here I have the incident light. So this is the point 1 where I am getting the reflected light, and this light may reflect inside, and again from the substrate it can get reflected back, and from this reflection again we are getting the interface, and again it will be getting refracted. So these two refracted light will be telling me, the light 1 and the light 2 will be telling me that what kind of film thickness I have. Okay, so these are going to tell me the different colors, and based upon the different colors I am going to find out the thickness of the given film. So if I have different thickness, it is going to give me different colors, because here you can see we have the phase gap in between the light 1 and the light 2. Either the constructive interference or the destructive interference is going to happen, and because of the constructive or the destructive interference I am going to get a particular color for this thickness. Okay, so if I am going to increase or decrease the thickness, the phase gap is going to increase or decrease, which means the constructive or destructive interference is going to have at a particular level of incidence angle or different level of incidence angle, which means if I am changing the thickness, which means I am going to get a different color. So tilting wafer also changes the color. Why? Because if I am tilting the wafer, the phase gap is going to change. So now I have to find out the different colors at a particular angle of the wafer only. I cannot tilt the wafer during the measurement process. So there is a question, if you see some beautiful color rings on the wafer with a CVD dielectric layer, what is your conclusion? So if I am seeing various colors on the dielectric layer, which means I have different thickness, which means it is not uniform. Okay, so color change indicates the dielectric thin film thickness is changing, and thus we know the film with the color rings must have the problem with the thickness uniformity. It is not very uniform, which is the most likely caused by a non-uniform thin film deposition process, right? So there is another question, why does the thin film color change when one look at the wafer from different angle? Actually I have already given you the answer. Okay, you can recall it, and again I am telling you, when we are looking at a different angle, the phase shift is going to change, and thus the wavelength for the constructive interference and the destructive interference is going to change, and thus it is going to change the color. Okay, it is important to hold the wafer straight when using the color chart to measure the film thickness, and if I am going to tilt the wafer, which is going to make the thickness of the wafer thinner. Okay, I need not to tilt the wafer during this process. This is a very important point. So now coming to the Spectro Reflectometry. So it is going to measure the reflected light intensity at different wavelengths. We need to know the reflected light intensity as well, because we are going to use it in various formulas, and we are going to calculate various characteristics with the intensity of the reflected light as well. So it is going to calculate the thin film thickness from the relationship between the reflected light intensity and wavelength. If I know what is the reflected light intensity, if I know the wavelength, I can easily find out the film thickness. Okay, so this is the reason reflected light intensity is a very important parameter that I need to know. Photodetector is more sensitive than the human eyes, and thus We are relying more upon the photo detector to detect what kind of wavelength that we have. Spectro Reflectometry can obtain much higher resolution and accuracy for the given film thickness. I hope now you know the reason. So the relation of reflectance and the wavelength, you can see the reflectance and the wavelength. If I am going to increase the wavelength, the reflectance is going to change, and here at this point I am getting the constructive interference, at this point I am getting the destructive interference. Okay, so here you can see if I have different wavelengths, 1 upon Zm minus 1 upon Zm plus 1 will be equal to 1 upon 2nt, and from this relation I can easily find out the film thickness. Okay, refractive index must be known, okay, and the wavelengths must be known, and I can find out the given film thickness. So this is a very important relation that you can remember. Okay, so this is how our spectroreflectrometry system would be looking like. We are sending the light to the substrate, it is getting reflected. So this is the UV lamp from where I am sending the light is going to this layer, and from here it is getting reflected, it is going to the substrate, it is again reflected from here. So now this is the light that came here, and again from this reflector it is reflected to this point, and from here also it is reflected, and here I have put the detectors. Okay, so this is actually my system of spectroreflectrometry. So there arises a question that many advanced thin film thickness measurement tools allow user to choose the refractive index of the film. If someone has mistakenly chosen the PE-TEOS USG film refractive index to measure the O3 TEOS USG film thickness, what will be the effect on the measurement result? We know that the output thickness is based upon the refractive index. If I am mistaking on the refractive index, the film thickness would not be an actual value. Okay, so to measure the actual value of the film thickness, I must know what is the actual value of the refractive index. If I am choosing the different value of the refractive index, film thickness would be different. Okay, since the anti always couple together, a wrong N will cause wrong T measurements. O3 TEOS USG is a porous film and has the refractive index about 1.44, and now it is slightly lower than 1.46 of PE-TEOS USG. So you can see the refractive index of both of them are different, so which means measured O3 TEOS film thickness will be slightly thinner than the actual value. Okay, so this would be the result of using a different refractive index, or if you have a slightly small mistake in the calculation of the refractive index, there would be a mistake in the calculation of film thickness as well. So now coming to the deposition rate. What is deposition rate? The name is telling me what it is. It is the thickness of the deposited film per unit deposited time. So how much thickness I am getting per unit time is my deposition rate. So we have the wet etch rate as well. What is wet etch rate? Wet etch rate is the thickness change after the wet etch upon the etch time. Okay, so whenever I have the rate, I am dividing it with the time. So now coming to the wet etch rate ratio. So now it is the thickness change of the CVD film divided by thickness change of the thermal oxide film. Okay, so now when I am using thermal oxidation, its thickness is changing, and when I am using CVD, then the thickness is changing. The ratio of both of them is the wet etch rate ratio. Coming to the uniformity. Uniformity is measured at the multiple points. If I have a wafer, at the multiple points I am going to measure the thickness, okay, and it is measured with the help of various parameters like the average, with the help of standard deviations, okay, and with the help of many other parameters, mathematical parameters as well. So the basic two parameters are the average or the mean or the standard deviation. We know mean is the sum of all of the parameters. Like if I am measuring the thickness, the film thickness at a lot of points, I am going to take the mean. I am going to take the sum of all of them, and then I am going to divide it with the number of points. Okay, so the mean is x1 plus x2 plus x3 so on up to xn divided by n, and the standard deviation is denoted with the sigma, and it is equal to under root x1 minus mean of x square plus x2 minus mean of of x square plus x3 minus mean of x square plus so on, xn minus mean of x square divided by n minus 1. Standard deviation of non-uniformity is sigma under root x. So now coming to the stress. Stress is actually the mismatch between the different materials. Okay, so if I have two materials which are having different kind of properties, if I am putting them all together, they are going to give stress to each other. Okay, so we are having two types of stress. First is intrinsic and second is extrinsic. So intrinsic stress develops during the film nucleation as well as the growth process, when the particular film is growing. Okay, in the intrinsic stress we have the single kind of substance. Okay, the stress in between the single kind of substance, and it is occurring during the nucleation and the growth phase. So the extrinsic stress is resulting from the differences in the coefficient of the thermal expansion of two different substances. If I have one layer over which I have one another layer, both of them will be having the different thermal expansion coefficient. So this layer is going to expand more and this layer is going to expand less, and due to which they are causing stress on each other if I am giving them higher temperature. This is extrinsic stress. So tensile stress is there and the compressive stress is there. Both of them are arising due to the intrinsic stress or the extrinsic stress. In both of them we are having the tensile as well as compressive stress. When we have the tensile stress, we are going to crack the film. Tensile stress is moving outward and the compressive stress is going to compress the film, and due to which we can form the hillocks. So you can see the film stress. If I have the bare wafer, the substrate would be looking like this. After the thin film deposition, if I have the compressive stress, I am going to get the negative curvature. If I am having the tensile stress, I am going to get the positive curvature. The substrate is going to bend. Okay, I am going to get a curvature. So you can see the illustration of the thermal stress at the 400 degrees Celsius. If I have SiO2 over the silicon, you can see the length is L and we have some temperature T. So at the room temperature, if this is my wafer, now it is cooled to the room temperature. So it is cooled, SiO2 and Si have different cooling rates, so now they are bending. So now this is that OL is the difference between the SiO2 at 400 degrees Celsius and SiO2 and the silicon layer at the room temperature. So this difference is equal to alpha, OT and L. So now what is alpha? Alpha is the coefficient of thermal expansion. Alpha of SiO2 is 0.5 into 10 raised to power minus 6 per degree Celsius. Alpha of silicon is 2.5 into 10 raised to power minus 6 per degree Celsius. So you can see both of them are having different alpha, and due to which they are going to expand more or less on different change of temperature. Okay, so now if I have Si3 and 4 nitride, it is having the alpha 2.8 into 10 raised to power minus 6 per degree Celsius. For tungsten it is 4.5 into 10 raised to power minus 6 per degree Celsius. For aluminium it is 23.2 into 10 raised to power minus 6 per degree Celsius. So how we can measure the stress? Stress is measured with the help of formula E upon 1 minus omega at square upon 60, 1 upon R2 minus 1 upon R1. Now if I am changing the wafer curvature, so R2 and R1 are representing the wafer curvature before and after the film deposition. So if I am changing them, stress is going to change. So laser beam scans wafer surface, reflection light indicates the wafer curvature. Okay, so with the help of both of them I can find out the stress. So this is my laser, this is my mirror. Okay, or the reflecting surface. Laser is going to send the light, and here it is going to reflect from the wafer and the thin film over it, and here I will be having detector. Okay, so these are the references. These are really amazing book. If you have any doubt or if you want to analyze this topic in the great detail, you can refer these books, and if you still have any doubt, you can put the doubt in the comment and I will try to resolve your doubt, reply to you as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel and also do share it with your friends. Thank you so much.